So what are they gonna learn today, apart from physics is boring? Last time we did pressure, so this time something new, pressure. So I'll tell them about how to calculate pressure and how to understand the experiments we just did last week. But to understand that, they need to understand what's a vacuum. I don't think they will understand that, for it's the 8th class, you know. But if they don't understand, they don't ask too much questions. So let's go on with the vacuum. Okay, so let's get very serious about this. To understand the experiments we just did in the last week, the ones with the Magdeburger Halbkugeln or Magdeburger hemispheres and the vacuum bell I've been uploading last week, we need to understand what is a vacuum actually. Actually, it's quite an easy concept. Let me show you. The definition of a vacuum is actually quite simple. It just says that a vacuum describes the absence of matter. And so in a perfect vacuum, there wouldn't be any particle of any kind at all. And therefore, it is just a theoretical concept which actually doesn't occur anywhere. And that means actually nothing else than there's just nothing. So far so good. It's quite intuitive to understand that on the spot where I am just right now, obviously, apparently, there is matter. Or on that spot. Matter. Made of matter. Even over here. Even Big Cookie is made of matter. But matter is not only containing solid state objects, like I am one, or Big Cookie is one, or for example that little stone is one. Even the space that seems to be empty in this room, like in between of all those objects, is actually filled with matter. This room, for example, is filled with a mixture of hydrogen, oxygen, and a small amount of noble gases, which we just call the air. Actually, I'm quite sure that a fair part of this room is filled with CO2. So that means, even if there's no solid matter around like Big Cookie, or that stone, or even me, the room is not evacuated. Because matter contains solid state objects like me, fluids like liquids and gases, for example the air around, or liquids like the water. The word evacuated, which I just mentioned. Really? Did he? Yeah, did he? I never listened to him. I guess it is quite familiar to you. Because when people need to get taken away from a certain spot or a certain area, maybe because of safety reasons or anything like this, they get evacuated either. And this is just what the vacuum pump does. Alright, let me clear this. Not that the vacuum pump evacuates people, but the vacuum pump evacuates, for example, the air in the vacuum bell. Or in the Magdeburger hemispheres. As good as it can. So to make sure that I'm not lying to you and that gases consists of matter indeed, I want you to pause the video and think about the assumptions of the model of an ideal gas. So I'm sure it was easy for you to remember that the ideal gas contains little mass points without a volume at all that do not interact except for little bumps among each other and between themselves and the wall of the ideal gas. And due to the change of movement of the little particles on the inside of that gas and the bumps among themselves and between the particles and the wall, forces are exerting. And all those forces, again, are the pressure that occurs on the inside of that gas. So if you remember that, which I'm sure you did, then you will definitely remember our satisfying animation of the model of an ideal gas we've been watching at when we had regular lessons. To check. Here we watch the 3 possibilities to change the magnitude of the pressure. Possibility number 1. increasing or decreasing the pressure by increasing or decreasing the temperature. Possibility number 2. Increasing or decreasing the volume of a certain amount of gas. And possibility number 3. Increasing or decreasing the amount of gas in a certain volume. And this is just what the vacuum pump does, as you will see in the following. It just takes out the particles of a gas of a certain system. And it will look like this. Let's have a look once more at our simulation of the model of an ideal gas. What we've got over here is our system, where we can increase the walls and the volume or decrease the volume. And we can heat our system up and cool it down. But as you can see, nothing of this changes the pressure of the system, for at the moment there are no particles on the inside of the system. So we pump in some particles here, as we've seen that a lot. These are some heavier ones, and I can even pump in some lighter ones. And as you see, apparently the lighter ones are the faster ones. So now we need to think about what would it look like if this pump here wasn't an air pump or a particle pump, if it was a vacuum pump. Of course it would look like this. First the particles are scattering around quite chaotically, and after we use the vacuum pump, the particles are streaming out because they get pumped out by the vacuum pump. So as soon as the system reaches a critical point of evacuation, one speaks of a vacuum. And for there are a lot less particles inside the system after evacuating it, there will be obviously a lot less bumps among the particles and between the particles and the wall. Which means that the pressure inside is a lot smaller than before evacuating. And your task will be now, first, to figure out the different types of vacuum, second, the magnitude of pressure that exerts in those different types of vacuum, and thirdly, the approximate number of molecules occurring in those different types of vacuum. Finished your homework? Alright, so let's keep going. Try to remember our little quiz we did in the regular lessons, where we figured out that if the pressure in a system is smaller, the arrows of the forces exerting in that systems are smaller as well. So this is one of two things we should definitely stick to. First, the higher the force that exerts, the higher the pressure. But let me give you an example for that. Et voila! Let's take these weights. We've got everything from 2 grams until 1 kilogram. Apparently, if I take the 2 grams over here and the 1 kilogram, if I take the 2 grams and put them on top of my hand, I feel a pressure that is actually almost not there. But if I take this 1 kilogram weight now and place it on top of my hand, due to the gravitational force, due to the gravitational force that is always exerting towards the center of the Earth, the occurring pressure will be a lot higher than the one if I would just take the 2 grams and place them on top of my hand. So now let's go to the second very important thing about pressure. And for this we use a little wooden plate over here and a screw. And maybe you remember I've been putting like 10 to 15 seconds ago that 1 kilo weight on top of my hand. We said, alright, there's definitely some pressure around and every one of you would feel the same pressure in my situation. But if we now take the same weight and place it on top of a screw and just assume the screw has got no weight itself, then you think if that wooden plate would be my hand, the pressure would be a lot higher and that would hurt a lot. Okay, so sit back, relax, but stay focused. We've just learned the 2 things to change the magnitude of the occurring pressure, right? And this is how we got for this. So, either we change the magnitude of the occurring pressure by changing the weight, and by doing so, we changed the exerting force on a certain surface. But there's a second way we discovered. So we figured out that the same mass exerting on a surface gives us a different pressure if we change the surface. That means a lower surface causes a higher pressure and a bigger surface causes a lower pressure. But let me show that to you on the cupboard. Alright, so what do we got over here? First, we got 2 little blue circles that should remind you of your 6 nice things to know about pressure worksheet, where we figured out the definition of pressure. Below the title, what is pressure? So the question we are going to answer today is how to calculate pressure. And for that, we need to stick to the idea that pressure occurs because of forces that are exerting on an object. So let's draw a little sketch with a red surface named A and the orange force exerting perpendicularly on that surface. And for we know that a bigger force exerting gives us a higher magnitude of pressure, we can assume that the force needs to be above the friction brake. On the other hand, we know that a bigger surface the force is exerting on gives us a smaller magnitude of the pressure, which means that the surface definitely needs to be below the friction brake. So let's finally talk about the unit of the pressure. Since we know that the pressure is divided as a force divided by a surface, the unit should be Newton for the force divided by square meters for the surface, which is just what we call Pascal. And this is what you already should know because of your homework you did. Okay, so my part is done for today. Please have a look into your Inhaltsbibliothek, look at the worksheet over there, do the tasks on it and just finish them before the holiday begins next week, so until Wednesday. And I hope at least you had a bit fun watching all those videos, because it was quite a big effort for me to prepare them and put them all together. And yeah, so see you next time. Bye bye. And don't forget to subscribe. Leave a comment over here. What? You gotta learn a lot, bro. And just leave me a